Welcome to this tutorial on sUAS and public safety operations. I'm Matt Schwegler with the Infrared Training Center. David Lee will join us here in a moment. Before we begin, just a quick announcement. If you're interested in attending any one of our infrared training and certification classes, you'll find a complete calendar on our website. Specific to today's topic, we now offer a public safety sUAS Level 1 certification course. Upcoming dates and locations for this, as well as any of our other classes, can be found online at infraredtraining.com/schedule. And for our fellow thermographers based in Europe, the Middle East, or Africa, head to irtraining.eu for the latest schedule and information on how to register. All right, on the line with me here is ITC's David Lee. He's one of our trainers, thermography instructor. David is an airline transport pilot, a certified flight instructor, and he's also host of the FLIR Delta series, which some of you should recognize him from. David's now one of the trainers here at the Infrared Training Center, and we're very fortunate to have him. And I wanted to say good morning, David. How are you? How you been?
Good, Matt. How about you?
Oh, doing really well.
Good. Excellent. Well, everybody, thank you for joining us today. This is a topic that I know a lot of people are interested in, and it's one that I've been working in both full-scale aviation and with drones since the late 1990s. My first 10 years with FLIR, this is what I taught to helicopter and airplane crews. So let's take some of those lessons learned on full-scale side and see how they apply to drones. So what we're going to be talking about today is on the screen right now. We're going to start out with just a real quick, what is infrared imaging? There are a lot of misconceptions out there about how these cameras work, what do they do, a brief overview of the different ways that thermal drones are used in different public safety applications. We're going to talk about how do we plan our flights in our heads. If you notice, the subtitle of this presentation was called "Thinking Ahead of Your Camera." That's a phrase that comes from when we would teach pilots to fly. We talk about being ahead of the aircraft. What that really means is you don't want the airplane to get somewhere your brain hasn't already been for 5 minutes. So we're going to talk about how we do that with a camera when we're flying on a drone. Basically, it comes down to what are the things we want to consider before we turn a blade, before we get off the ground. Some of that's going to be environmental factors. Some of that's going to be what's the nature of your camera? What's the relationship between your field of view, the angle at which you're looking down from the drone, and the altitude you're flying at. And we're going to talk about how do we calculate a maximum theoretical detection range, and I'm going to show a pretty good example of this done not well and this done well. And so let's get started. All right, so what is thermal imaging? It's important to remember that even though we in the industry often use temperature as kind of a shortcut, these cameras don't see differences in temperatures. They see differences in radiation. Infrared radiation is part of the electromagnetic spectrum. It's given off by everything above absolute zero. And really what we're looking at in these pictures on the right are relative intensities of thermal or infrared or heat energy. Those terms are often used interchangeably. Just because something's got more heat energy in it does not, or looks like it has more heat energy in it, does not necessarily mean that it's hotter or colder than something next to it. If we look at this tanker truck, for example, we can see that the top of it looks very, very cold, or the bottom of it looks hotter. These aren't necessarily different temperatures. The difference is that this is giving off less radiation because it's reflecting the cold sky. And here you're going to see these this image pair here. We've got a good difference in temperature, difference in energy between. When we don't have thermal imaging it's just, if I could have you take away anything from this part of the presentation, it's to remember that what these cameras show you is a picture of radiation and relative intensities of radiation, not temperature. Okay, we see radiation, we calculate temperature. And how things are going to look is going to be impacted by what it's made of, what's around it, what's its exposure to the sun and weather, and sometimes how hot it is. And finally, what I want to emphasize is that thermal imaging is a surface phenomena. We don't see through much of anything. Okay, so for instance, a question we get quite often is, can I see through leaves? If somebody's lost in a forest, can I see them through the leaves? No. Short answer. But we're going to talk as we go along here about what are some things you can do to kind of work around that and still have a mission with a good chance for mission success. Okay, so what are some of the applications that we're using thermal drones for? Well, obviously firefighting. I've carved this up into two different things: structure fire and wildfire. Structure fire thermal is really good because it can see through smoke. For monitoring personnel around a fire, the incident commander can get live video feed of where all their people are around the fire, obviously not in the structure, but around the structure. And then it can provide information on the integrity of the structure for attack groups or for ventilation crews on a roof in areas that might be in danger of burning through. Now, I should mention that our UAS folks, Brett Kanda, did an excellent webinar. I believe it was on Tuesday of this week, Monday or Tuesday, with LA Fire Department, and that should be recorded and available online for you to watch if you want a real deep dive into fire applications in particular. They did an excellent job on that. So another thing to think about with firefighting is forest fires or brush fires. So there's a lot of ways that a thermally equipped drone can be useful here. One is obviously giving the incident commander an overview of the area that allows them to not only keep track of where their personnel are, but to deploy their crews more effectively. It's also really good for trench and wetline integrity. You want to make sure that your boundaries don't have gaps in them, so you can find places that may have areas of the fire that have escaped containment. And finally, it's a really good tool for predicting the movement of a fire, so that you can evacuate members of the public before structures and lives are really in any significant danger. And now obviously this isn't the only tool in the toolbox for that, but it's one of them that provides a lot of supporting data. Now the last area for forest and brush fires is hotspot mop-up after the fire. This video, and you can see right here, there's actually a ground crew that is looking at the feed from the drone. This is a fire that when this was taken, was out for almost 4 days. There was no visible fire at all, but as we run this video, you can see lots of hot spots that are under the ground. These can smolder for days and days and days. And if somebody walks over, maybe hits them with a shovel or a pick, get some oxygen in there, they can flare up in a hurry. So it's really important to use a drone with thermal imaging to help fire managers take care of all of these hot spots so they don't flare up again. All right, so one of the other areas that we're seeing use for thermal drones is in law enforcement. Now, this isn't like this video I'm going to show was taken from a helicopter, and obviously drones are not going to have the same applications as helicopters, at least in this point in their development. They don't have the range. We have beyond visual line of sight restrictions, all these sorts of things, but they can be very effective in setting up perimeter security. If you've got a fugitive search and track going on, they're very effective for that. And as we watch this video roll, we can see that not only is thermal imaging good for keeping track of suspects and officers, it's also good for evidence search and recovery, as we watch right here where this gentleman throws a gun up onto the roof, right there. And this is with a much older system. You can see this was taken back in 2006, but it's with a system that is actually from the late 90s. So the technology that we're using in drones is actually more advanced than this now. So right along with law enforcement is search and rescue. Search and rescue, I kind of put these together for a couple of reasons. One is that search and rescue can be handled by a number of different agencies. It can be handled by a fire agency. It can be handled by a law enforcement agency. It can be handled by civilian volunteers. The common thread between law enforcement and search and rescue is often what we're trying to do is find and or track a person. Okay, so with search and rescue, the big benefit is that it allows visual contact with a victim in a way that no other technology can. Day, night, we can get that information with GPS coordinates on the screen back to incident command, and they can use that to more effectively deploy their personnel. Now, another advantage of drones in this application is to search large areas, and maybe you've got some really rough terrain, and you want to maybe not put your foot crews up there yet, or maybe you've got horse crews, you don't want to put them in that area. So you can eliminate large areas and put your manned crews in areas with a higher probability of finding the victim. So where do we start? Well, we start before we take off. We need to, this is what I talk about thinking ahead of your camera. We need to think about what's the target we're looking for. What are the weather conditions? What's the physical environment? Meaning, is it flat? Is it hilly? Is it downright mountainous? Is it heavily wooded? What kinds of woodland are we looking at? Are we looking through deciduous trees, or are we looking through evergreens? And then what are the tools we're working with? Specifically, what's the resolution of your camera and the lens of your camera? Because these are all going to go into how far away you can detect a person's heat energy, and that's what we're trying to do. So when we talk about target information, we're talking about a number of different things. We're talking about the size of that person. We're talking about, in a second, why that's really, really important when we try and calculate a possible detection range. If we look at this picture here, that's me standing next to a young woman. You can see that my thermal signature is taking up more pixels in this image than hers are. So we have to think about that in terms of, is the person we're looking for male, female? Are they large? Are they small? Are we looking for an adult? Are we looking for a child? Are we looking for an animal? You know, if we're looking for a group that was on horseback, then maybe it's going to make more sense to try and find the horses, because those are going to be bigger targets. Well, we can use that to calculate our detection range. And then also, you know, maybe we're looking for an abandoned vehicle. If we look to the left of where I'm standing here, we can see a large SUV. Obviously, that's a much larger target to look for. So all these things are going to go into play when we're deciding how we're going to plan and fly our missions. Now, other things to think about: are they healthy? Are they sick? Do they have a mental condition that could cause them to behave erratically? Things like that. How are they dressed? Are they prepared for the weather? Meaning, if it's really cold outside, are they insulated? Right? If they're insulated, then by definition, they're going to be giving off less of their heat. If they're not prepared for it, then we may have a window where they're giving off a lot of heat relative to their surroundings, but we have to worry about them, if they're out there too long, becoming hypothermic and giving off less heat. Now, all of these things, when we put them in our heads and start thinking about them before we take off, we need to think about these are things that can influence our detection range. They can influence how far away we can see somebody. Okay, well, there's another group of things we need to think about. We need to think about the environment, because all of these things can also, so things that impact the difference in apparent temperature or heat energy between the target and their surroundings. Okay, things like cloud cover, precipitation, something we're going to talk about in a second, called solar loading. All of those things are going to impact what we call a delta T, or a difference in apparent temperature. And again, that's kind of a shorthand. We're really talking about heat energy here. And then there's things that are going to interfere with our direct line of sight to the target. And that's where we get back into vegetation, okay, and topography. If we're in, you know, the Great Plains of America, where it's really, really flat, we would fly a mission differently than if we're in the Rocky Mountains. Okay, simply because of the changes in vegetation and the changes in topography. So some of those environmental considerations, let's start with one called the diurnal cycle. Diurnal cycle is just a fancy name for the sun going up in the morning and then the sun going down. And when the sun comes up, it's going to start bathing the earth in its energy, and the earth and everything on it is going to start absorbing that solar energy. When the sun goes down, if it's a clear night, all that energy is going to radiate off. Now, if it's a cloudy night, it's not going to radiate off as much. Okay, so we need to keep in mind, where are we within the diurnal cycle, and how is that going to impact our ability to detect a human target. The next is solar loading. Okay, this is we'll get back to this image pair here for a second. Let me tell you about this set of images. This set of images was taken in very close to identical conditions. The temperature was in the low 50s Fahrenheit, clear days, low humidity, really ideal circumstances. And in each one of these, the sun had been over the horizon for less than 30 minutes. If I remember correctly, it was about 15 to 20 minutes actually. And these are, by the way, both pictures of me. And if we look over here, you can see me clearly at 150 feet. Here, if you didn't see this shadow here, you may not even know I was there, and this was only 30 feet away. Now, there are only two differences in why my heat signature looks so different in these images. They were taken with the same camera, on the same drone, with the same settings, and I'm not kidding you, I was even wearing the same clothes. Okay, so I tried to do everything possible to make this an apples to apples comparison. The difference is what I'm standing on. Okay, this is largely bare earth and rock. There are some tufts of scrub grass over here, but it's largely bare earth and rock that's absorbing a lot of that solar energy, that even though that the sun hasn't been up much, it's still absorbing that thermal energy and cutting down on the apparent temperature difference between me and my immediate surroundings. Over here, I'm standing on nice, thick, spongy grass. Now, I said there were two differences. The other difference is that in the picture on the right, this was high desert. As soon as the sun came over the horizon, the surroundings and me were exposed to the rays of the sun. The picture on the left, the sun was over the horizon, but it was not yet over the tree line. So this picture on the left was not exposed to direct solar load. Okay, so if you're doing a search and you're doing it in the daytime using thermal, you have to keep in mind, where am I in the diurnal cycle? What is the environment I'm in, and what are the possible implications of how long this person has been exposed and their surroundings have been exposed to the sun. Okay, so that's what we call solar loading. Now, the next one to talk about is kind of a derivative of solar loading called thermal crossover. If we look at this picture here, we've got a person and their dog walking on grass, and we're in the white hot color palette, or what's called white hot polarity. Okay, and the person looks warm compared to their surroundings, right? White hot. If it's whiter, it's hotter, right? Okay. But as we run this video, we'll see that they get over here, and now they start looking darker because they're on the concrete. Well, now they get into the shadow, and they start to look hot again. Okay. And as we run this forward, we'll see what happens. They're still looking white hot, which is as we would expect. But as they get back over here towards the asphalt, you'll notice that all of a sudden they look colder than their surroundings. Now, their surroundings haven't changed. They haven't changed. Go back to what we were talking about, looking at relative intensities of thermal energy. That's what's changed. They are giving off less energy than what's around them. Now they get up here on the grass, and they virtually disappear. If they weren't moving, they'd be very, very hard to see. Okay, so all of these differences are taking place in the same scene at the same time with the same subjects. So these are just things we need to keep in the back of our heads. These are things that are going to influence how far away we can see a human target. All right, so let's get down to this. How far can we see? Well, as we've already talked about, there are a lot of things that are going to impact this. First off, the distance at which we can see a given target, it's called its range, or more specifically, as we're going to talk about here in a second, its detection range. And there are a lot of variables that go into that. Atmospheric conditions, the lens and resolution in the camera, the nature and size of the object. But then if we're going to get a little more esoteric, we need to talk about what does it actually mean to see a target. Well, in the late 50s, early 60s, the government actually came up with a criteria for that. It's called the Johnson criteria. And it's a criteria to develop to model the effective range of infrared cameras. And it sets out 3 criteria for quote unquote seeing a target. It's detection, recognition, and identification. Now, let's start at the end here and say, now, of course, when we're talking about a thermal camera, we're not talking about facial identification. We're not talking about saying, oh, that's Matt out there in that field. Really, the way these things developed was detection would be a dot, recognition would be, oh, that's an armored vehicle, and identification would be, oh, that's an M1A1 tank kind of thing. So that's the sort of delineation we're talking about. But the way these things are defined is by the critical dimension of the target, and we're going to define that in a second, and how many pixels are covering that critical dimension. For detection, we're only talking about 2 pixels. Recognition is defined as covering 6 pixels, and identification is defined as covering 12 pixels. Let's take that a step further. With each one of those, you've only got a 50% probability of detection. So let's say we're in the recognition realm. We've got an adult human is defined by the Johnson criteria as being 1.8 meters high by 0.5 meters wide and has a critical dimension of 0.75 meters. Okay, so if we're going to look at recognition of that person, we would want to cover that critical dimension with 6 pixels, and let's say we're looking at them from a kilometer away. Now this is obviously outside the realm of what we're going to do with our drone cameras, but I did that intentionally just to hopefully not have anybody hanging their hat on that number. This is strictly to illustrate the idea. Okay, so if we met all of these conditions, covering that critical dimension with 6 pixels at 1,000 meters, that still means you've only got a 50% chance of seeing them. Okay, now what can cause that? This is really a human factors sort of thing to think about. Are we looking at the right area of the screen? Okay, how tired are we? Did somebody walk up and start talking to us right when those 6 pixels blipped onto our screen? All of those things, it's kind of a fudge factor to say you're not going to be perfect. Okay, you've got a 50-50 shot of actually recognizing that as a human target as opposed to, say, a Sasquatch at a kilometer when you meet those criteria. Okay, now a couple more things about the Johnson criteria. It is extremely optimistic. It doesn't take into account atmosphere. It doesn't take into account thermal contrast. It doesn't take into account the lens you're using or the electronics that were used to build your camera, or what's called the system, the signal to noise ratio, which is going to affect how much noise is in the image. All that means is if we're going to use the Johnson criteria, we kind of need to fudge it a little bit. And what I do personally is I double the number of pixels for every category: detection, recognition, and identification. So instead of 2 pixels for detection, which would look like that at the top, 6 pixels for recognition, and 12 for identification, I use 4, 12, and 24 for my calculations. Okay, just to give me a little more wiggle room, because potentially a person's life is on the line, and we don't want to be overly optimistic when we're planning our flights. Okay, so what does that mean? Well, that lets us figure out what a ballpark detection range might be. If we take our target size in feet, because we're in the US, and the IFOV, which is the instantaneous field of view in radians, this is a specification you can look up for your camera. The IFOV is, in thermography, the IFOV is defined as the angular coverage, of what a single pixel can see. In Johnson criteria, they take that a step further, and this is going to be important here in a second when we talk about this. The IFOV is defined as the angular coverage of a single pixel at the center of the field of view. Okay, so again, this is a spec you can look up. It's usually specified in what are called milliradians, so you have to convert it to radians, but it's pretty simple to do. Okay, so target size, this is our CD in feet, divided by the IFOV in radians, and then we're going to multiply it by 50%. Okay, and that's going to give our maximum detection range in feet. So a person's critical dimension, again, that's defined by Johnson criteria as 1.8 meters by half meter, or 0.75 meters. We convert that to feet, we get 2.475. Now the IFOV for an XT, an XT2, a View Pro, a Duo Pro 2, with a 640 resolution and a 13 millimeter lens, that iPhone. This is information you can look up on the website or on the camera's documentation that you get with it as well. So if we run the numbers for a single pixel, we could see a single pixel theoretically at 1,892 feet. But remember, the Johnson criteria is talking about 2 pixels for detection. So to get that, we have to multiply this by half, and we get 946 feet for the 2 pixel detection. Oh, remember I said that I personally would rather use 4 pixels for detection because it's more reliable, so we have to do that again. I'm going to round that number up and say that our safe detection range is going to be 500 feet for this system and lens, resolution and lens. Now again, remember, this isn't taking into account weather, it's not taking into account solar load, it's not taking into account any of that other stuff. In a perfect world, we're talking about 500 feet. So what does that really look like? Well, here's me at 50 feet. There's me at 250. There's me at 500. Right there, yeah. A lot of people look at this picture and their eyes are first either drawn to the lamppost or the trunk of the tree over here, but that's me right there. And that's, if you analyze that picture, that's roughly 4 pixels across the critical dimension. That'd be pretty tough to see, right? Especially if you've been flying a lot, you're getting a little fatigued, if there's a lot of activity around, if the incident commander saying, hey, what do you see? That kind of thing would be pretty easy to miss. But there's another thing here. Look at the altitude I'm flying at. Look at the look angle. I'm really flat to the horizon, aren't I? That maximizes my critical dimension because I'm looking pretty much straight at myself. But it's not really realistic. Okay, I'm in the Pacific Northwest. 150-foot fir trees are in everybody's backyard. Okay, so I'm not going to fly a search like that. I'm going to be up higher. So what happens to our critical dimension then? Well, it gets smaller, doesn't it? There's me at 50 feet. There's me at 150 feet. That's about the same number of pixels as we got at nearly 500 feet on the previous slide. Okay, so keep in mind how a person's critical dimension is going to change as your look down angle changes. When we talk about look down angle, a 0-degree look down angle would be parallel to the ground. A 90-degree look down angle would be perpendicular to the ground, or what's called nadir, okay, looking straight down. So target size or a critical dimension changes with look down angle, but also how much ground you can cover at a time is going to change with your look down angle. That's called the camera footprint. We need to talk about that too. Okay, so your camera's footprint on the ground, meaning how much ground your camera is going to cover, is going to change with altitude, look down angle, and your lens and resolution. So if we look at this for a 640 camera with a 13mm lens, and again, we figured our safe detection range, just as reference, was going to be roughly 500 feet. Now, keep in mind, this number is what's called the slant path, okay? It's the hypotenuse of the triangle. It's not the distance you're seeing on the Go or Pilot app, okay? It's the actual distance, slant distance from the camera to your target, okay? So if we look at this with a 60-degree look-down angle, we get a footprint that looks like this. Notice it's not a rectangle. This would make you think the resolution of the sensor and the field of view specs that you see in the spec table would make you think that we're going to see a rectangle. Well, we're only going to see a rectangle if we're looking straight down, right? The flatter we look out, the more elongated this trapezoid becomes, and we'll see that in a second. But also notice, and I know it's hard to see, I didn't do a real good job at choosing my colors. The circle with an X in it is where the center pixel is in your detector. Remember, our definition of instantaneous field of view, or IFOV, for the Johnson criteria is how much can a single pixel cover at the center of the field of view. Now watch what happens as we flatten our look down angle. This is at a 60-degree look down angle, pretty close to looking straight down. There's a 45-degree look down angle. There's a 30-degree look down angle. Okay, notice what is happening in our relationship between the top of our field of view and the center of our field of view. If we look at our 30 degree compared to our 60 degree look down angle, the top of our field of view, meaning the top of what you're seeing at the top of your iPad or a monitor, whatever kind of monitor you're using, is much, much farther away from the actual center of the field of view as you look at a flatter look down angle. Okay. So again, if we're at 150 feet over the ground at a 60 degree look down angle, we're looking basically 180 feet away. At a 30 degree look down angle, we're looking 300 feet away. Okay, so what's the takeaway here? The takeaway is that if we are predicating our detection range, let's focus on the blue box here, which is our 30 degree look down angle. If we're predicating our detection range calculation on the pixel at the center of the field of view, a good 3/4 of what you're seeing on your iPad or whatever monitor you're using is thoroughly outside of our detection range. In fact, even for the 30 degree field of view, a lot of what is right at the center of the field of view is outside of our detection range. The only one in this scenario where we meet our detection range criteria is the 60 degree look down angle. Okay, so consider how this is going to impact things. If you do that back of the napkin calculation and say, okay, for this flight, I'm going to assume that I can detect a person with 4 pixels across the critical dimension from 500 feet. And then I go out and start flying, and I'm continually changing my look down angle. Okay, you can be very easily, once you get past about 45 degrees, if you're at 300 or 400 feet above the ground, you can very easily fly right over somebody and not even see them, simply because the geometry of what you're asking, you're simply putting yourself physically in a position where you can't detect that target. And that's obviously something we want to avoid. So again, shallow look down angles are going to maximize your target size because you're looking flatter to them. You've got more pixels to work with, but it can render much of your field of view outside of the safe detection envelope. And what we're seeing here, I should have explained this earlier, is this is where the aircraft is right at where these lines cross. And this is 500 feet down range. This is 1,000 feet down range, 1,500, 2,000 feet. So we're saying in this scenario that the center of our field of view is at about 700 feet down range. Okay, and all of the rest of this is beyond our detection range. Steeper look down angles are going to have a lot more useful content because you can control what's within your detection range easier, but you're going to shrink the target's critical dimension accordingly. So maybe instead of 500 feet, you need to plan on 300 feet, depending on the situation and the target. All these things are just things you don't want to be thinking of mid-flight. You want to have these things in the back of your head before you take off. Okay, so how far you can see is really a balancing act between your theoretical detection range, which is that calculation we did earlier, the solar load, the weather, and the foliage or tree cover. So here's something of me, again, in pretty much ideal conditions. And I've got evergreen trees right here. You'll notice that as soon as I go under that tree cover, I'm gone. And even though I'm still walking around back there, it's hard to see me. This is just an editing blip. So I go down a little farther, so I'm looking at more of an angle. I also changed color palettes here. Now penetration, but I've got another, I walked the same path on both of these mock-ups, and you can see a little bit of movement back in there. Every once in a while, some of my energy gets through the tree cover, and you can see me. Okay, so again, if you've got an area where you can look at a flatter angle, look straight down through the tree cover, you're going to have a different chance of success. And really what you'd want to do if you're trying to cover a wooded area or an intermittently wooded area is you'd want to do both. You'd want to fly a flight where you're looking straight down, and then you want to go back, change batteries, and fly a flight where you're looking at a flatter angle like this. Okay. Now here's a real world example. This was actually done, This is one of the earliest actual search finds with 8 with by a gentleman rescue in the Alps, and he had found this victim right here, who was a mountain biker who had been caught out after the sun went down and was disoriented, lost, starting to get cold. So the drone pilot, and I didn't want to cut in, an hour, but the drone pilot had found the victim. The victim was in cell phone contact with the incident command, and they put a 4-man team up at a trailhead that would get them close, and then the drone pilot was guiding the recovery team here into the victim. Now, in this case, we've got deciduous trees, but it's fall. The leaves have fallen. We're able to see through them a little bit more. Now, you notice he's just switching back and forth between black hot and white hot, and he's guiding the search crew down here to the victim. Now, he's taking it, again, this is Switzerland, this is in the Alps. He's taking advantage of the fact that he's letting the topography work for him to allow him to see diagonally through the trees a little bit better. And then he looked up and realized he was about to run out of battery and needed to scoot home. But anyway, that was actually a really good example of how this can be done correctly. All right, so in summary, before you take off, understand the target you're looking for, the environment you're working in, that has to do with cloud cover, sun exposure, time of day, all these sorts of things, and then what are the mission parameters, and then plan your altitude and look down angle to maximize your chances for detection. So, Matt, that's all I've got. Do we have any questions?
First question had come in from Luis. Was research and literature available on the probability of detecting a victim of a crime, let's say, somebody who is deceased? Is there anything in that realm or things that you've heard of with that for sUAS, the sUAS platform?
Boy, that's interesting. So if we're talking about someone who is deceased, there are a couple of bits to that. One is that obviously, how long have they been deceased? Remember, we're seeing differences in radiation. If there's no longer any body heat, then that becomes very, very tough. Now, I do know that there is some research ongoing in a couple of labs where they are they're actually tracking the decay rates of bodies as they decay and how that gives off energy and can sometimes create a thermal difference. I don't believe, at least I haven't heard of, I could be wrong, I don't believe any of those studies have concluded and been published, but I know that research has been ongoing in a couple places around the country.
Let's see, we had a question from Nicholas. What should be the best mark or sign to wear to indicate that one is a researcher versus a target? I think this was referring to a point you had made earlier. I guess clothing or things. Do people wear certain reflective clothing or certain emblems or something that is something available, I guess, that makes a person stand out if that's something that's needed?
Oh, in terms of like a search team member as opposed to the victim?
Yeah, is that done? And do they do that? And what kind of materials will they use if that's even done?
Not in terms of passive materials that I know of. I suppose theoretically they could wear things that are reflective to infrared, and that may show up differently. Typically, people are working in teams. And so there's an interface between the drone operator and the incident command about where different teams are. But I suppose if you're looking for a group of people, that could become an issue of trying not to confuse the two. I know that in the manned aircraft world, it's not unusual for search teams to wear, or at least one person within a search team to wear what's called an IR beacon, which is going to give a little timed flash of infrared energy that can be seen with the camera. I don't know of civilian groups that are using that because they're kind of expensive. But I have heard about that in the past. Typically, I believe though that in all the scenarios I've been involved with, people get around that confusion simply with procedure and knowing where their teams are versus where the drone is in the search pattern, or the manned aircraft for that matter.
Had a question from John that came in. What if a search is being done to someone who has been exposed in a cold climate? I guess if you're out there and you're lost and it's a cold environment, if your body temperature is dropping, I know there's issues with, let's say, a parka where you have extra layers of clothing on there. The question really is, how can you maximize, contrast in that situation? Working with different color palettes. Any tips for someone in that situation?
Okay, yeah, that's an excellent question. So if, like let's say out here in the West, if we're doing a search in the mountains, what would I try and do to maximize my detection rate? Bundled up. First is assuming that you've got a daytime waiver, try and fly at night if you can. Do so legally, obviously. Another is, when it comes to color palettes, stick to white hot and black hot. We see a lot of people who kind of who are new to thermal imaging and kind of get enamored with all the colors. But there was one of the Delta videos I did where I actually showed that using different color palettes than black hot and white hot can decrease your detection range up to a factor of 4. I believe it was the rainbow color palette. Instead of seeing a truck out to about, I'm not entirely sure I remember the numbers correctly, but let's say it was 2,000 feet. We could only see it. And so, yeah, if you look at footage from military aircraft or from law enforcement aircraft, you'll notice that all they're working with is white hot and black hot. And it's not because those sensors aren't capable of using color, it's because they're not as effective. So yeah, that's the big thing is use white hot and black hot color palettes. And
couple more questions that came in. You were talking about viewing angle there before, flying at 90 degrees versus 45 degrees. What is the recommended best practice for viewing angle when flying? This is from Brian.
Well, that's okay. That's a good question, and that's kind of one of the takeaways from this is there isn't one. It's going to depend on the conditions you're in. Okay, what's the terrain you're flying over? Is it hilly? Is it flat? What kind of vegetation? Are the deciduous trees? Are they evergreen trees? All that stuff is going to play a part. This is just going to come up to personal preference as you practice a lot with your equipment. You find out what works best in your environment. If I'm looking at an evergreen forest in a hilly terrain, I'm trying to look between 45 and 60 degrees. Okay, I don't want to get flatter than 45, and I don't want to get steeper than 60. Are there going to be situations where maybe you're looking in a canyon and you have to change that and look straight down? Absolutely. But again, that's all going to be dictated by the terrain you're flying over.
Let's see. How does using isotherms and alarms assist with searching for subjects? Does that work at all?
That's something we see quite a bit now. For people who don't know what an isotherm, or in thermography cameras, they're called temperature alarms, are. That's a capability within an app or a camera to have a certain temperature range set. Let's say you're looking at a grayscale palette. Maybe you have it set to display as a yellow or a red. Again, I'll go back to military and law enforcement helicopters, or aircraft. These systems have a lot of processing power. They could certainly do that. They don't, because it's not effective. And the reason it's not effective is because the temperature alarms or isotherms are based on a temperature. Let's say you want to put in, now the mistake we see a lot of people make is oh, I'm going to put it in for 98.6 degrees and we'll find a person. Well, 98.6 is your core temperature, not your skin temperature. And there's going to be some variation in skin temperature. There's also going to be some variation. What is the temperature of the clothing that the person is wearing? Because that's really what you're seeing, except for their head. And then if you don't have things in the camera that are set up correctly, like emissivity, you're not going to be looking at the right temperature anyway. So can isotherms be used as a tool in your toolkit? Sure, they can. Don't run out on the first search you go on and rely on them, because they're not going to, and I see this online quite a bit, people saying, oh, the isotherms will just find a victim for you. Well, they won't. In fact, you can, if you set them up incorrectly, they can blanket an area with that color, and then you'll actually lose the temperature difference that you're trying to see within that isothermed area. So really, my personal recommendation is stay away from them. Can they be made to work? Yeah, but typically where they're going to work is in a condition where you're going to see the person just fine anyway. Okay, kind of like me standing in the grass. An isotherm would work perfectly there because there's good definition in energy between me and my surroundings. But you know, you can see me just fine anyway. If you look at a picture of me where you can't even tell where I am, the isotherm is going to be painting that entire area orange or red, and you're not going to see me there anyway. So I say my recommendation is stay away from them. They cause more problems than they solve.
Good question here about lens.
That's my soapbox.
Nah, no, it's perfect. Good question here about lens choice. Is there a general rule of thumb for selecting the appropriate lens for various missions, whether it's search and rescue, fire, agriculture, roof inspection? Is it safe to start with a 13 and go to the 19 millimeter? What are your recommendations for lens choice?
Actually, I would preface this by saying we need to talk about resolution also, because if we have, for instance, a 13 millimeter lens with a 640 resolution camera, we're going to have roughly a 45 degree field of view. If we have that same 13 millimeter lens on a 336 resolution camera, we're going to have a 25 degree field of view. So think more in terms of what's the angular coverage you're after. Now, the applications that were mentioned are actually quite different in terms of what you want to achieve. Looking at doing roof inspections, you can get away with them with a much wider field of view and simply fly lower. So you have good coverage and you also have good detail. For search, where you want to balance is not get so wide that your detection range, it gets down to 50 feet or something like that. But at the same time, situational awareness, and the phrase for that is looking through a soda straw. It becomes very hard to keep track of where you are in your search pattern with, for instance, the 25 degree field of view, or the 25 millimeter camera that's available for some of the XT2s and Duo Pro Rs. Personally, if I'm flying with a 640, I'm going to use a 19 millimeter lens. If I'm going to be balancing between search type applications and industrial applications, then maybe I'll go to a 13. But my default is going to be a 19 for a 640.
Excellent. Perfect. I think you've answered everyone's question really well, Dave. I really appreciate it. I think we're going to wrap it up on that.
Okay, great.
Remember, you can catch this presentation on demand at infraredtraining.com/webinars, where we have about 24 other topics as well, all free and available for viewing at any time. Of course, all of our upcoming training dates and locations in the US and Canada are posted online at infraredtraining.com/schedule. For those of you in Europe, the Middle East, or Africa, head to irtraining.eu for the latest list of classes in your region. Thank you for attending today's session. We'll see you online again soon for our next tutorial from the Infrared Training Center.